Hello and welcome. We have arrived to the second lesson on the unit of derivatives where we will explore and discover the formula for the derivative of a polynomial function f of x equals x to the power of n. We'll use the first principles formula for it. And as a matter of fact, I've already prepared a video about the proof of the derivative of a polynomial function. I attached the link to the video here so you can click on it or you can scan the QR code. So it is very important that before you move on to the examples, you listen to the video. And I would like to also mention that it is very important that we go through the proofs of any theory in mathematics in general because, well, for many good reasons. But first of all, exposing ourselves to the process of developing a proof helps us understand the depth of the concept. And not only that, but it helps us understand the agility of a formula or the theory. And all these together will help us develop more intuitive ways to approaching solving problems that are related to this formula. So I'm going to move on now to the examples, but I do strongly encourage you that whenever given a chance, just go over the proof and not just memorize the formula. It's not about memorizing. We have a limited capacity, right? So in memorizing things, but we have an unlimited capacity in finding connections between things. And that's what proofs do for us. So as you probably actually saw in the other video, in the proof video, the derivative of a polynomial function of the form f of x equals x to the power of n in prime notation will be f prime of x equals n times x to the power of n minus 1, where n is a number. Now, the way that we just wrote the derivative with a little apostrophe, we read it prime, is what we call the prime notation. And today we are going to talk about a new way of denoting or expressing, communicating the derivative of a function, Leibniz notation. So as we have mentioned in class, Leibniz is a very famous mathematician that have invested a lot in the theory of calculus. And he came up with a new notation of a derivative. So, and this is what it looks like, d dx. So if you look at his notation, I'm just going to do something different. So when we say d dx, this is just another name for this prime in here. So it means the derivative of a function differentiated in terms of x, right, of the function f of x. So that's Leibniz notation, and it's equivalent to saying f prime x. So both mean the same thing. And you're probably thinking and wondering, so what does Leibniz notation do that f prime doesn't? Now, we are at the beginning of the theory of calculus, and we are going to, as we learn more about it, so we're going to learn how to differentiate functions that are a lot more complicated than purely polynomial or purely rational. So we're going to learn how to differentiate functions that are combinations of all these groups of functions we're familiar with, and we're going to do this in this course. But further to this, very often we will have to differentiate a function that is made of more than a function, and we will have an overlap of the independent variables. So what Leibniz notation does, it tells us exactly in terms of what independent variable we are differentiating a function. Okay? And with examples, I'm pretty sure, and I hope, and I'm pretty sure that this will become clearer and easy to do and will come naturally to us. So this is one form of Leibniz notation, but just like we say f of x or y, sometimes we say d dx of y. or we simply say dy dx. All right, so we're going to move on to the first example, f of x equals x to the power of 7. I'm going to do it in both notations. So in prime notation, we say f prime of x equals 7, x to the power of 7 minus 1. Obviously, you don't have to show this step normally, but I'm just showing the work because it's our first lesson on it, but you can just write the answer 7x to the power 6. In Leibniz notation, we will say that d dx of fx is actually d dx of x to the power of 7. So notice that when we are using Leibniz notation, it's important that the independent variable you see in the function matches the independent variable that you have in the derivative notation, in Leibniz notation, right? So that would equal, and this would be differentiated in the exact same way. So we're going to say that 7x to the power of 7 minus 1, or 7x to the power of 6. I know that you're probably thinking that, oh, but this seems like a longer way, so how is this making my life easier? But there will be situations when this is going to be a must use, right? And it will help a lot. But right now, we want to use it in these simple functions so that, or simple derivatives, because that's how we are going to kind of naturalize ourselves with it, okay? So in the next example, I simply ask to find the derivative of u to the power of 8 in terms of u. So that's straight Leibniz notation. So you're simply going to write here 8u to the power of 7 minus 1. I'm sorry, 8 minus 1. I had my answer in my mind. So 8u to the power of 7. Okay, so we're going to move on to more examples. Now just ignore this part here. I was trying to do something else there. So the constant rule. So the constant rule states that if f is a constant function, so a constant function is in the form f of x equals c, or y equals c, or y equals a number, right? Then the derivative of it will be 0. Or in other words, we're going to say that the f prime of x equals 0. I always appreciate a nice rectangle. And d dx of c equals 0. So can we prove this? This is an easy proof. You can do that very easily, but let's just do it together. So if f of x equals c, then we're going to say that we can also write f of x as c x to the power of 0, right? Or if I want to go back, we're going to say it would be c times 1. Right? That won't change the expression. Or c x to the power of 0. So what that means is that this exponent now will become a coefficient. So we're going to say that that would equal c times 0 times x to the power of 0 minus 1. This is purely power rule. So c times 0 is 0, x to the power negative 1, which is 0. So we say that f prime of x would be equal to 0 for the constant function. And now remember again, what does the derivative of a function tell us about the function? What kind of information does it give us? It gives us how fast the function is changing, okay? So how fast the y values are changing, and are the y values changing in a constant function? You're going to say, well, it seems that they're going in the same direction. The line is flat. The y values aren't changing. So it makes sense to say that f prime of x is 0 in here. Now, the constant multiple rule states that if we have a function gx multiplied by c f of x, then the g prime would be c times f prime x. Kind of hard to see that like in a definition. It's easier when we apply it into formulas. So we're going to say that if we have the function gx equals 8 to 8x to the power 3. So the 8 will stay there. The only part that we differentiate will be the x to the power of 3, which is going to be in itself 3x to the power of 3 minus 1. So that will make the derivative 24x to the power of 2. In the same way, and you can try this on your own without waiting for me, so kx equals 6x to the power of negative 5 over 3. So the derivative of it will be 6. So 6 will stay out of the game for now. And then you simply differentiate the x to the power negative 5 over 3, which will be negative 5 over 3x to the power of negative 5 over 3, take away 1. So 6 times negative 5 over 3, here we have negative 10x, and up here we have negative 5 over 3 minus 1, which is negative 5 over 3 minus 3 over 3, or negative 8 over 3. Now, very often we will insist that you write the answer with positive exponents because that is considered to be the most simplified form. And we're going to say that the final answer must be k prime x equals negative 10 over 8x to the power of 8 over 3. Now, the sum rule tells us that if both functions f and g are differentiable, then the derivative of the sum of the two functions, so you add them and then differentiate, will be equal to the sum of their derivatives. And here's the Leibniz notation for it. The difference rule is very similar to the sum rule because sum or difference are within the same kind of family, okay? Because difference can be seen as a sum of two things with opposite signs, right? So let's practice this in a few examples in here. So we have g of x made of so many terms added and subtracted to each other. So we're going to say g prime would equal 15 times, let me make this a little bit bigger, 100x to the power of 99, 1 power less, minus 3 times 12x to the power 1 less than 12, 11, plus 5x to the power of 1 less than 1, so 0. And then minus 46 is a constant. Remember that the derivative of a constant equals 0. Okay, so we're going to say that this will turn into 1500x to the 99 minus 36x to the 11. And 5x to the power of 0 is simply 5. And this will be the derivative of this polynomial function. The next question is kx equals 2x6 minus 7x to the negative 6. So I brought in some negative coefficients to keep us company here. But I just wanted to actually bring them into our examples to indicate that the power can be a negative number, and that's okay. We can still use the power rule formula. So we're going to say k prime x equals 2, and then 6x to the power of 5 minus 7 times negative 6 x to the power of negative 6 minus 1. So this will turn into 12 x to the 5, and then 7 and 6 will multiply, well, they will make a positive 42, because they're both negative, x to the negative 7. If we want to write this with a positive power, then we're going to have 12x to the 5 plus 42 over x to the power of 7. So that's k prime x. Next example, and by all means try to do these questions on your own because you can, and then you can follow with the solutions here. So h prime of x equals, so you see that we have an interesting power in here. Don't be afraid of it. It's just a number. It will become a coefficient. Leave it in exact form. That is very important. X to the power of pi minus 1. and then minus square root of 2x to the power of root 2 minus 1. This will be the exact form, and we can't simplify any further, so that would be the answer. Okay, and we want to write the derivatives with exact coefficients in exact form. Now, we're going to make our examples a bit more interesting. Why not? So the next example, number 7, we have tx. So we're finding t prime of x. Now, when I have interesting powers like these ones here, I would like to convert them into normal powers. So I want to write the whole equation as x to some power, or every term in the equation as x to some power instead of the roots. So what we want to do first in this case is rewrite the equation of the function we're differentiating. So tx equals x to the power of half plus 9x to the power of 7 over 3, and then minus 2x to the power of negative 2 over 5. So just to emphasize one more time in here, so the index, when you don't see it, is 2. That becomes the denominator in the exponent. So this index here is 3. Again, that's the denominator in the exponent. The index here is 5. That's the denominator in the exponent. Now, as for the minus sign here, it comes from the fact that the x in here is in the denominator. So it's coming up to the numerator. It makes it easier for us to differentiate it. Okay, I hope this makes sense. And I'm just going to write the formula in here. Just remember that if you have the number a to the power of m, the nth root of it, that would equal a to the power of m divided by n. And it doesn't matter if you write it as the nth root of a to the power of m, or if you write it as the nth root a, everything to the power of m, it means the same thing. So keep this formula handy, write it down somewhere in case that sounds not so familiar. So now we are ready to differentiate. T prime x equals 1/2 of x to the power of 1 over 2 minus 1. I'm showing the steps here. Obviously, you can do this a little faster, right? And with practice, things will get better. X to the power of 7 over 3 minus 1, and then minus 2, x to the power minus 2 times negative 2 over 5, x to the power of negative 2 over 5 minus 1. So you see, wherever you see those exponents that are not in rational form, you give it a denominator of 1. And then you make them into, so multiply by the lowest common here. So here by 3 and here by 5. Okay? So we get in here t prime x equals 1 over 2 x to the power of, so here we have 1 over 2 minus 2 over 2, so that must be negative half, plus 9 times 7 over 3 would be 3 times 7, 21, x to the power of 7 over 3 minus 3 over 3, that's 4 over 3, and the last coefficients will multiply to 4 over 5, x to the power of negative 2 over 5 minus 5 over 5, negative 7 over 5. Okay? So if you want to write this with positive exponents, then we'll say this would be 1 over 2, x to the power of half, plus 21x to the power of 4 over 3, plus 4 over 5, x to the power of 7 over 5. Okay? So we're moving on to the next example. So this time we have y equals x minus 2 over root x to the power of 2. We have a little bit of work to do here because we have a binomial to the power of 2. which means we need to expand this. So this will turn into the first term to the power of 2. Remember, we're using the formula a minus b squared equals a squared minus 2ab plus b squared. That's how we expand a binomial power 2. Minus twice the product of the first term with the second. And then plus the second term squared, which is 4 over x. So even better, we're going to say that y equals x squared minus 4. So here you have a power of 1 with a power of 1/2. So that would be x to the power of 1/2 in the numerator. And then plus 4x to the power of -1. You got to bring it up, right? So you got to bring the numbers from the denominator up. Whereas here we simplified power of 1 with power of 1 over 2. So 1 minus 1/2. So now we're going to find the derivative, and I'm going to write dy dx in here, okay, which is nothing but d dx of x squared minus 4x to the power of half plus 4x to the power -1. So this would be the derivative of the first term is 2x. Derivative of the second term is -4 times 1/2 x to the power of 1 over 2, take away 1, right? And then plus 4 times -1 x to the power -1, take away 1, okay? And here, just to make things fair, so we are subtracting 1 from each power. And now we'll simplify. We have 2x to the power of 1 plus 2x to the power of -1/2, and then minus 4x to the power of -2. So with positive exponents, you would write dy dx equals 2x plus 2 over x to the power of 1/2 minus 4 over x to the power of 2.